Today we're going to be looking at a new topic which is called energy balance. So for energy balance, we are not going to look at in detail, in depth. We are just going to be you are just going to be introduced to a few concepts of energy balance, how energy balance are carried out, and why is it important. The first thing when we talk about energy balance, similar to the first time when we mentioned mass or material balance, we said that we have this law of conservation of mass. So since we have a law of conservation of mass, we also have one for energy. Here we are saying that energy can neither be created or destroyed. Okay, this is the first point that everybody, I think most of you have heard, that we cannot create or destroy energy, but energy can be transferred from one system to another system, or energy can change its form. So for example, the easiest example I can give you is that, let's say this is in your house, you can have let's say this is your light bulb. Okay, this is your light, and then when you click on the switch, let's say this is your switch, right? If you click on this, what will happen? There will be an electrical energy, okay, electrical current. In terms of current, the electrical energy will be supplied to your light, and the light, there will be light. Okay, so here we are saying that your energy, the electrical energy, is actually changed from into light energy. And then sometimes after a while, you can see that if you go and actually touch your light bulb here or your light, you will feel that it is hot. So meaning that some of the electrical energy is converted to heat energy, right? Because it is hot. So that is how you can change a form of energy from electrical energy in the beginning to light energy, so heat energy. Meaning that it is changing form, but it cannot be created or destroyed. Okay, the second point is that the amount of energy gained by a system must be exactly equal to the amount of energy lost by its surrounding. Okay, so if you see here again, we have this term system and surrounding. Okay, we have looked at this definition of system, surrounding, when we were doing material balance in the beginning of our class. So these definitions still apply for energy balance. So let's say in terms of our chemical processes, let's say this is our system, right? So you can have an open system or closed system, right? Depending on your situation. So if this is your system, everything else is your surrounding, right? And we can have, let's say this is your open system, right? You put your boundary, right? This dotted line we can say is your boundary. So everything here is your system, everything outside the boundary is your surrounding. So this is saying that if, let's say, your system is gaining energy, so I can just put here E is gained by the system, so the same amount of energy must be lost by its surrounding. So meaning that if your system is gaining 100 energy, so the surrounding is losing 100 energy, meaning that it is input equal to output. So the same thing here, if your system is giving away energy, the exact amount will be obtained or gained by your surrounding. So this is what we call law of conservation of energy, and this is known as the first law of thermodynamics. So if you are interested to learn more, there are a few laws of thermodynamics which deals with energy, entropy, and all these things. So when we are talking about energy, we will be looking at first law of thermodynamics, which says that energy cannot be created or destroyed. It can only be transferred from one system to another system, or it can be changed into another type of energy. So this is just a refresher for everybody. I hope you still remember all this terminology and their definition. Again, we have the definition of system. It's an arbitrary portion of a process or part of the process that you consider for analysis, right? So as I mentioned just now, if let's say this is your system, right, we can have open system or closed system. So this, if you have input and output, so this will be your open system, where material and mass and material crosses the boundary of the system. Okay, and when we are dealing with energy balance, we have to add another thing. This definition for open system was only for our material balance. Now, since we are dealing with energy balance, we add another point here. We're saying that material or mass and energy. Okay, so let's say this is our boundary, right? Okay, this is our boundary. So we have, in open system, we have our mass flowing in and out of the system. And when we are dealing with energy balance, we have another point we say saying that energy is also flowing in and out of the system. So material and energy crosses the boundary of the system. Okay, that is for open system. So we are just adding a little bit more to the definition of open system. The second one, we have a closed system, which can be our batch system, right? So for closed system, we already agreed and we already know that no mass exchange occurs to the surrounding, right? Whatever you have in your system, it's a closed system. So whatever mass you have, it will stay in your system, right? So that is why there is no something going in and nothing is coming out in the system. But that is for mass. But when we talk about energy, even if it's a closed system, we can still have energy going in and going out. There will still be flow of energy, or energy can be transferred in and out of the system. So this is the two differences between mass and energy balance. Okay, when we are talking about the definition of open system and closed system for material balance, these two are the definition. But when we are talking about the definition of open system and closed system for energy balance, this is still correct. But even in for closed system, there will be there will be exchange of energy happening in and out of the system. Okay, so those are the additional terminologies that you have to understand. Thing is that steady state still the same. We say that the condition remain unchanged with time, so no accumulation. Unsteady state, the condition changes with time, so there is accumulation in the system, right? And then we'll be looking at, I think we also covered this one, but properties are the durable characteristic of the system, such as pressure, temperature, volume, mass, all the things. So the property of the system, so moles, pressure, temperature. So when we're doing mass balance, we did not worry about what is the temperature, what is the pressure. We were just concerned about the mass or the moles of the system. So when we are doing energy balance, we have to consider what is the temperature, what is the pressure, because all these things will affect your energy balance. Okay, and then what is equilibrium, meaning that thermomechanical phase and chemical properties of the system are invariant, meaning that it won't change with time. Whatever temperature or the mechanical or the chemical properties of a system in equilibrium, it will not change with time. Okay, and then we have another terminology which is called phase. So which is defined as our physically distinct, meaning that if I were to write to you until now, if I were to write to you, this is H2O. Until now, we have done several problems for reactive or non-reactive material balance problem where we're dealing with H2O. We were only dealing H2O as a chemical species, right? So we did not care whether the H2O was in liquid form, whether the H2O was in vapor form or the H2O was in solid form. So for material balance, we will only concern that this is H2O. This is water. Either it's vapor, liquid, solid, it does not matter. But when we are dealing with energy balance, we want to know whether this is liquid, whether this is gas, or whether this is solid. Why? Because there will be some energy related when we change from liquid to gas, gas to liquid, liquid to solid, solid to liquid, or solid to gas. There will be some energy associated with this. So the next thing is that these are some new terminologies that are important in energy balance. The first one is that we have what we call adiabatic system. Adiabatic system means that a system that does not exchange heat with the surrounding during a process. So let's say if you have a process, so this we are talking about new terminologies that are related to energy balance. So if you have a process, let's say this is your system, a process is occurring. So if you want to make sure your system is in adiabatic system, so you have to make sure that there is no heat coming in, no heat going out, no energy flow in and out. If that is the case, you have to, then the system will be adiabatic system, and we can have that when we have, it is called perfectly insulation. So you will have a layer of insulation to make sure that there is no energy being transferred in and out. Okay, that is for adiabatic system. For isothermal system, is a system which temperature does not change during a process. So again, same here. So sometimes we don't want our system to be static, we don't want, but we want our system to have a constant temperature. So if we want to have a constant temperature, so we call that system as a isothermal system, meaning that at the beginning is the same temperature, in the middle of the reaction is the same temperature, and at the final of the reaction is the same temperature. So the T here is a constant, temperature is constant. So how do we achieve that? Meaning that sometimes we have to supply some heat to the system to make sure that the temperature is constant. If the temperature is too high, you remove some heat. So depending on your condition, but ultimately you want to make sure that your system is at a constant temperature. The next thing is that you can have an isobaric system in which pressure does not change during the process. Okay, and then finally we'll have isochoric system in which the volume does not change during the process. Okay, so both of these are interrelated, because if you have pressure does not change, sometimes volume can change. If volume is not changing, pressure can change. So these are 4 types of system you can have, and we can deal with energy balance. Okay, the next thing that it's important for us to know is that what is variable and what is path variable. So variables are all the things that we know. Okay, so for state variables, any variables whose value depends only on the state, meaning that state here it can either be temperature, pressure, composition, volume, and so on and so forth. Okay, so for example, some of the variables that we can call as state variables are our internal energy and enthalpy. So if you remember your steam table, right, you can have let's say at 100 degrees Celsius, and you can say 1 MPa, right, from your steam table, you will have a value of internal energy, your enthalpy, and so on and so forth. And if I change the temperature to 200 and 1 still pressure the same, the internal energy will change. Or I have 200 degrees Celsius and 5 MPa, right? So it will change the internal energy. So it means that with the changes in your condition, right, the condition here, so temperature, pressure, all these are the condition, it will cause the value of the state variable to change. So that is the meaning of state variable, and it does not depend on how the process occurs. So let's say, for example, in this you have at state 1, right, and then you have at state 2. So it doesn't matter how it get to state 1 to state 2, as long as the condition at state 1 and the condition at state 2 are same, meaning that your value will be the, okay, so it does not matter whether it is at state 1 or at state 2, does not matter how you get to from state 1 to state 2, as long as the condition does not change, the value will not change. Okay, so for example is your internal energy and enthalpy. The second variable with your path variable. Path variable is any variable whose value depends on how the process takes place. And the best example for path variables are work and heat. Okay, so if you look at here, this is your first condition, this is your first state, this is your second state. Okay, so at this first state, you want to go to the second state, meaning that here you have two ways to go there. Either you can take the path A here, which will reach to point number 2, or you can take path B, which will get you to point number 2 as well. But since the path is different, meaning that the value will be different for your path variables. So if, let's say, I can say that maybe when I'm talking about work, so if I want to go from point 1, which is here, to point 2, which is here, I have to do extra work because I have to go up, then I have to turn right. So more work need to be done. If the value is not same, so it is called a path variable. Because if you see from point 1, if I take this path B, I can see that I have to do less work, meaning that this is a path variable. Okay, so those are the difference between your state variables and path variables. These are important when you are actually doing the energy balance calculation. So it is important because you need to be able to identify which one is your path variable, which one is your. Now we have looked at all the terminologies, right? We have looked at what is your open system, what is the closed system, what is the adiabatic, isothermal, isobaric, isochoric system. Now we look at the form of energy. Okay, so for form of energy, you can have energy that can be transferred from the system. Okay, so let's say again this is your system. So the form of energy can be divided into one form that can be transferred to the system and from the system. Okay, the other form of energy is the energy that is possessed by the system. Okay, so two forms of energy, one can be transferred in and out, and one that is possessed by the system. So the first form of energy that can be transferred from system to surrounding or surrounding to system is known as heat. Okay, so heat energy is the form of energy that can be transferred due to the temperature difference between the system and surrounding. Okay, so for example here, if you have, let's say, if you look at this example here, right, this is your fire. Okay, so at this fire here, if I were to label here, the temperature will be higher. Let's say the temperature is 200 degrees Celsius, right? Fire is hot, and then heat will be transferred. So this pot is your system, right? This is your system. I can label here as so heat energy in form of heat will be transferred from here to your system. Why? Because initially when you have water, so let's say your temperature, ambient temperature water will be around 28 degrees Celsius or 30 degrees Celsius. So meaning that the energy from high temperature will be transferred to a lower temperature. So if you see here, due to the temperature difference between the system and the surrounding, meaning that, so all this is your surrounding, everything here is your system. And then heat can only be transferred from high temperature to low temperature. So temperature difference here meaning that you have 200 degrees Celsius and 28 degrees Celsius. So there is a difference between these two temperature, and because of that, then heat energy will be transferred from high temperature to low temperature. So the next thing is that the value of heat energy will be positive when the heat is transferred to the system, meaning that if the system is gaining energy, you are gaining something, so you are positive. But if you are giving something, so if let's say another example, what is the example for system that is giving up heat? Is that let's say you have a hot cup of coffee. Okay, this is hot water. Okay, hot cup of coffee. This temperature might be 100 degrees Celsius. Outside, so again this is your system. Outside here, everything here, the ambient air is at 25 degrees. So meaning that energy will be transferred from your system to the surrounding. So if you are losing something, then the heat energy will be negative. Okay, and then it will be zero again if you remember the adiabatic condition, meaning that there is no heat transfer. So it will be zero for condition. Now, heat transfer can occur by conduction, convection, and radiation. So if you look at briefly here, a figure here, conduction, convection, radiation can happen simultaneously, or it can happen one at a time. So all these things will be covered in your second year. So for now, you only need to know the form of energy, which is heat. The second form of energy that can be transferred to the system and to the surrounding, known as work. Okay, work is a form of energy that represents a transfer of energy between system and surrounding due to force, torque, voltage, and other things. So to put it in a simple way, whatever energy is transferred not by heat is work. Okay, so you only have two ways to transfer heat to the system or from the system to the surrounding. One is heat, one is work. So we know that if it's dealing with temperature, it is heat transfer, energy transfer by heat. Everything else, pressure, torque, voltage, force, we know is a form of energy transfer known as work. So that is the easiest way for you to understand. If it's dealing with temperature difference, it is heat. Other than that, it is work. Okay, the same thing here. When the value is W, okay, the symbol for work is W, is positive. The work has been done on the system, meaning that you are doing a work, you are putting in energy into the system, right? And the value of W is negative, the work has been done by the system, meaning that the energy is being removed from the system to the surrounding. Now, for these two point here, it will depend. Some reference book will say that when the work is done by on the system, the value will be negative. Okay, some books say it will be positive, some books say it will be negative. So it depends on how you look at the system. Sometimes there's people will look at it in a different way, so they will say that when the work is done by on the system, so it is negative because why? You have to put work on the system, so you have to put more work, which is negative. But when the work is done by the system, so it is positive because you are gaining something from the system. So it's a matter of perspective on how you look at the system. So either way, both definitions are correct, telling you that sometimes in some reference book, when the work is done on the system can be negative and can be positive, and the work that is done by the system can be negative or positive. Okay, depends on how you look at your system. Okay, so work can be defined as mechanical work, electrical work, shaft work, or flow work. So mechanical work is the work that occurs because of a mechanical force that is moving the boundary of a system. So the easiest way is that if you have a piston, right, that is a mechanical work that is happening. Okay, a piston is moving up and down, so it is the boundary of the system. Okay, so this is the formula for work. Work is a integration of force times ds, and s is your distance. Okay, so this is just an easy equation for you to know. The next thing is that electrical work, okay, occurs when a current pass through an electrical resistance in the circuit. So you can have work done by electrical current. The next thing is that shaft work occurs by a force acting on a shaft to turn it against mechanical resistance. So it's in the work, okay. And then it's the flow work performed on the system when fluid is pushed into system by the surrounding. You can have it the other way when the fluid is pushed out from the system to the surrounding. So that is based on the flow of fluid in the system. You can have it fluid is going into your system, and you can have fluid leaving your system. Okay, so most of the time flow work is usually related to your open system, where you can have material going in and material coming out. When you have that, you will have this flow work. So now we have looked at form of energy that can be transferred to the system or to the surrounding from the system. Now we look at the form of energy that is possessed by the system. The first one is kinetic energy. So kinetic energy is the energy due to the translational motion of a system. So if you have movement, then you will have kinetic energy. And the equation for kinetic energy, I'm sure that everybody is familiar with this equation. EK, so E is the for energy, K is the reference for kinetic energy, is equal to half mv squared, where m is your mass and v is your velocity. Okay, so this is a very basic equation for kinetic energy. Now kinetic energy can also be converted into specific kinetic energy. So when we're talking about specific kinetic energy, it's just that whatever value of kinetic energy you got, you divide it by mass. So if you do that, you'll get specific kinetic energy. The next energy is potential energy. Energy due to the position of a system in a potential field. So right, so if let's say you have, let's say this is the waterfall, right? If you have a height of h, then we can say that if you are jumping from this waterfall, then you'll have a very high potential energy. So it is due to the position that you are at. And then the equation is EP, P stands for potential, is equal to mgh. M is your mass, g is your gravitational acceleration, and h is your height of position, right? So the same thing here. If you can have specific kinetic energy, you can also have specific potential energy, which is potential energy divided by the mass. The next one is that internal energy. Okay, internal energy is a macroscopic concept that takes into account all the molecular, atomic, subatomic energy in the system. Okay, or we can say in an easier way is that all the energy possessed by the system other than kinetic and potential energy. So in your system, you can have possessed by the system, you can have kinetic energy, potential energy, and also internal energy. And internal energy must be calculated from certain other variables such as pressure, volume, and temperature, right? Because we said that your internal energy is a state variable. Okay, the same thing here. If you have specific kinetic potential energy, you can also have specific internal energy, which is internal energy divided by mass. Okay, and then finally you have another form of energy, which is enthalpy. So enthalpy is a combination of your internal energy plus your pressure and volume. Okay, so it's a measure of total energy of a thermodynamic system. So it's a combination of everything. The product of internal energy plus the energy required to expand the system into the environment, thus the environmental surrounding. Okay, so the formula for internal energy is this one. H is equal to U, internal energy, plus PEV. P is your pressure, V is your volume. So if you know your internal energy, if you know your pressure, if you know the volume, then you can find the value of enthalpy. Okay, so those are the forms of energy you can have. You can have energy that can be transferred to the system, the surrounding, and from the system to the surrounding in terms of work and heat. And then you can have energy possessed by the system, which is kinetic energy, potential energy, and also internal energy. And then the other form of energy is enthalpy, which is the total energy of a thermodynamic system. So those are the form of energy. So the next thing that we will look at is that a little bit a basic on the energy balance on a closed system. Okay, so we already mentioned just now that if a closed system, there will be no mass flow in or out from the system, right? There's no mass flowing in and out, but we say that energy can be transferred in terms of heat and work, right? And then since most of the time your closed system will be unsteady state. So if it's unsteady state, you will have accumulation in the system. So the accumulation here is the difference between the final and initial energy of the system. Okay. So remember, we have our general material balance equation: input plus generation minus output minus consumption is equal to accumulation. So if I put right here, input plus generation minus output minus consumption is equal to accumulation. So we will never have generation and consumption terms for energy balance. We will only have input minus output equal to accumulation. And if it's a steady state, then there will be no accumulation. But for a closed system, so when we are in our case here, we are looking at closed system, unsteady state system. So if it's closed and unsteady state, you will have input minus output equal to accumulation, and this equation we can write it is equal to final system energy minus initial system energy is equal to the net energy transfer to the system. Okay, so from here we can change this equation into this equation. Now we can define, okay, initial energy of the system is the energy possessed by the system at initial. So you'll have UI, which is the initial internal energy, initial kinetic energy, and initial potential energy. At the final state, you'll have final internal energy, final kinetic energy, and final potential energy. And the net energy transferred to the system, we know that only the energy can be transferred by either heat or work. So we can say that the net here can be Q plus W or Q minus W. So this W, the plus or minus of W here depends on your definition of W. How do you define W to be positive? Is it work done by system positive or is it negative? So based on that, you can have, so both are correct, Q plus W and Q minus W. Okay, and when you do balance, you substitute everything into the equation. UF minus UI plus EKF minus EKI plus EPF minus EPI is equal to Q plus W. And then finally you get delta U plus delta K plus delta P is equal to Q plus W. So this is your final equation. And then this equation is known as the first law of thermodynamics for a closed system. Okay, so if you are interested to actually know how to actually derive the equation in detail, you can always refer to our reference book. Okay, and one more important part is that each term represents the respective net accumulation of energy over a period of time, and it is not energy per unit time, meaning that here our delta U here, which is UF minus UI, is between the time T1 and T2. Okay, the unit for energy is not per time, so you must understand this very big difference. Okay, so once we have this equation, we can use this equation to solve for energy balance on a closed and unsteady state system. So if we have other like say open system, we cannot use this equation. This equation is only for a closed unsteady state system. Okay, so we must satisfy all these conditions, meaning that there should not be any mass flow in and out, but there can be energy from the system or to the system. So if we satisfy those conditions, then we can use this equation to solve our energy balance problem.